Hello and welcome to a new topic in chemistry. Our focus today, as you can see, if you're watching this video, the original date it was assigned, it is Unit 10, Day 4, May 11th. Go ahead and start setting up your notes. And what we're focusing on today is something called colligative properties. It's a fancy sounding word, but we'll break it apart and see what that word actually means. But here's the essential question that we will be answering during this video lecture. How are the properties of what's known as vapor pressure and osmotic pressures and melting point and boiling point affected by dissolving a solute in a solvent? So when you have a solution instead of just a pure solvent, how do these properties change? How are they affected? That's our focus. So it does look kind of like a long and fancy EQ, but we will break the notes down into these different things, but this is just what it all looks like together. So vapor pressure, osmotic pressure, melting point, boiling point, those are all examples of colligative properties. All right, finish setting up your notes. If you need more time, go ahead and pause the video. Otherwise, come on back when you're ready. Let's get into it. So colligative property by definition it's a solution property which depend on the concentration of solute particles rather than even what the identity of it is. So the idea here is that it doesn't matter that this is potassium chromate and this is calcium chloride. They would have the same kind of colligative properties because they are both a 0.1 molarity solution. 0.1 molarity. And that's kind of an interesting thing that we really haven't talked about before. Like, shouldn't these two solutions be really different? But think about it. They both have the same amount of moles per liter. This would have 2 positive ions and then a third ion that was negative, so 3 ions floating around. This has 1 positive ion and 2 negative ions, so 3 ions floating around. So they have the same amount of particles, they're just a different identity. So the idea here is that because they're the molarity and the same number of particles in the solution, they would have the same kinds of colligative properties. That's what this means. Okay, because this is a new fancy sounding word, I want to make sure you process this. So I already want you to do a level 1 question. So a level 1 question related to this definition of colligative properties. Pause the video, come on back when you're ready. All right, first we're going to talk about vapor pressure lowering. So first of all, we need to make sure we know what vapor pressure is, right? So if you have pure water, there are some water molecules right on the surface of that liquid that are turning into gas particles. And that's because there's energy right above that liquid. So those top molecules are gaining enough energy, they turn into a liquid. And then they are creating some vapor pressure right above that liquid. So vapor pressure is the gas pressure above a solution or any type of liquid due to the solvent particles evaporating. Okay. Well, it says right away that the colligative property is called vapor pressure lowering. So spoiler alert, we already know that the vapor pressure is going to be less when you have a solution compared to when it's a pure solvent. Well, why might that be? Let's think about that. If we need the solvent to evaporate to create vapor pressure, if there's a solution, remember the solvent is dissolving something. It's busy, right? So if you have an aqueous solution, so this is trying to show you that there must be some type of solute mixed in that gives it this blue color. The aqueous means it's water mixed with whatever the solute is. The water is attracted to the solute. It wants to stay in the solution. So because the solvent particles are attracted to the solute, less of the solvent wants to leave by turning into a vapor. So this will have less vapor pressure than pure solvent will. Because this pure solvent, there's nothing extra keeping it as a liquid, so those top particles can turn into a gas. But in here, those top layer of water molecules, they are attracted to the solute, so they want to stay where they are. So less of those water molecules are turning into a vapor, so less vapor pressure, meaning vapor pressure lowering. So if you have a higher concentration, there will be more solvent solute attractions. So then that would be even less vapor pressure is the idea. So remember, colligative properties are based on the concentration. So if there's more higher concentration, more particles for the water to attract to, more vapor pressure lowering. Okay. The other one we're going to talk about is called osmotic pressure. All right, osmosis might be a word that you remember from other science classes. Basically, it's this idea that a solvent passes through a membrane that only the solvent can pass through. The solute can't fit. So here it is. Here's your original YouTube. Okay, so this is your semi-permeable membrane, meaning the solvent can pass through it, but the solute, these purple particles, can't. That's what this is showing you, right? So if you count it, 1, 2, 3, 4, 5, 6, there's still 1, 2, 3, 4, 5, 6, and then it has the same number on the right side also. So the idea here is that osmosis says the solvent can pass through it, and that's going to change the concentration. So this has the same particles, more solvent, concentration would be less. This has same particles, less solvent, this concentration just got higher. Well, that could be a process. So osmotic pressure says how much pressure is needed right here or right here to prevent osmosis, or how much pressure would I need over here to push that solvent back through the membrane so that I have reverse osmosis. Think of it that way. So if I want osmosis to happen in the opposite direction, how much pressure would I need to add, or how much pressure would I need on both sides so that there is no osmosis happening? That's kind of the idea about osmotic pressure. So pressure is like the vapor or the gas pressure right here, how much is needed so that this solvent level won't change. That's the idea. All right, let me make a connection to that to a math equation. So the math equation for osmotic pressure is the symbol of pi, not as in 3.14, whatever. This is just the symbol for osmotic pressure, and it equals capital M, capital R, capital T. Now, maybe you remember this from our gas law unit, PV equals nRT, because osmotic pressure is pi, so that's P for pressure. And then if you divide both sides by V, you would end up with really nRT over V, but molarity is moles over volume, right? Moles per liter. N is moles and V is volume. So when you divide both sides by V, you get N over V. Well, that's just capital M. So that's where that's coming from. So P or pi is your osmotic pressure, and the units will be in ATM. So you need to make sure that your R constant value is the ATM one. Capital M is molarity. R is liter atmosphere over mole Kelvin as the units, and then 0.0821. So remember, this is the whole thing that gets plugged into R. These are the units that go on this number for that Raoult constant, the guy who came up with, did a bunch of gas experiments and came up with this constant. And then remember, the temperature has to be in Kelvin. So you take a Celsius temperature, add 273, kind of some review stuff, making sure that that's fresh in your mind. So, of course, molarity will be in moles per liter, so that will cancel if it needs to be. Temperature will be in Kelvin, so that will cancel. You'll be left with atmospheres, which is what we measure osmotic pressure in. Okay. All right. So now we've got a math equation for osmotic pressure. Let's do an example. Here's a little backstory. Curing meats is basically what you do is you put a lot of salt on them. And the reason that works is because the salt pulls the water out, and then the natural like microorganisms or bacteria or germs, they can't grow because the water is gone. Typically, we do this with 20 grams of salt, 100 milliliters of solution. So that would be what we create. So we create a solution with 20 grams of salt and then 100 milliliters of solution. And then you can put the meat inside that solution. And then a little bit higher than room temperature, a little bit warm. What osmotic pressure would be needed to keep the water from going back inside the bacteria? So we're preventing osmosis. What pressure do we need to keep this meat preservation system at? That's the question we're answering. All right. Well, we know that pi equals MRT. So we need to know moles per liter. R is a constant, and we need to know the temperature, but change it to Kelvin. Let's do this problem. So here's my equation. Curing meats is done with 20 grams of salt, 100 milliliters of solution, temperature is at 28 degrees. What osmotic pressure is needed? All right, so we know that molarity, capital M, is moles per liter. We have 20 grams of salt, and it's implied because it's used with food. We're going to say it's sodium chloride. So I take 20 grams of sodium chloride. I add up the molar mass of 1 sodium and 1 chlorine, 58.44. I cancel grams, so I put grams on the bottom. I get to moles. That's what I'm looking for the top part of molarity. And I don't worry about sig figs because this isn't a final answer. Then I take the 100 milliliters and I turn it into liters because the definition of molarity is moles per liter. 100 divided by 1,000, 0.1. And again, I don't worry about sig figs. This would really be 0.100 if it needed to. I divide that out. I have the molarity is 3.4. So I can plug 3.4 into molarity. R is a constant, right? 0.0821 liter atmosphere over mole Kelvin. And then T, I take my 28 degrees Celsius plus 273. That's the conversion to get to Kelvin. So now I've got my M times my R times T. So pi equals osmotic pressure equals molarity times R times my temperature. So I know it's little, but take a look at this. Capital M is really moles over liter. So liters over moles cancel. K divided by K cancels. I'm left with ATM, which is the unit of pressure that I'm looking for. Multiply all the numbers. And then when you get the number on your calculator, we can only keep 1, 2 sig figs, 1, 2 sig figs. This has 3 sig figs, but we limit with 2. So I need to keep the system. So like a pressure cooker or a fancy freezer or something like that. I had to keep pretty high pressure to prevent the water from just naturally going back into that bacteria if I want to keep my meat safe, right? That's the idea. So again, making kind of maybe a strange kind of connection, but something in your actual world, preservations of foods, definitely could be thinking about pressures and temperatures, and the solution that they are putting the foods in could all be determined with colligative properties. All right. Okay, go ahead and take a pause and think about that example we just did. Think about vapor pressure lowering, think about osmotic pressure, do a level 2 kind of question. Pause the video, think about those notes so far. Come on back when you're ready. All right. The next colligative property we're going to talk about is boiling point and freezing point. So first of all, once again, spoiler alert, I'm telling you that the colligative property of a solution will mean that the boiling point will be higher, elevation. Okay, so what does that mean? The solution boiling point will be higher than a pure solvent. Okay, all right, so why does that happen? Think about what's happening to make something boil. The particles need to gain enough energy so they break apart from each other and turn into gases, right? So I have to break the intermolecular forces between the solute and the solvent so that you get enough solvent to evaporate to create enough vapor pressure. That takes more energy. The solute and the solvent want to stay stuck together. That's why they made the solution in the first place. So you have to break apart that attraction before the solvent can turn into vapor, create enough vapor pressure to overcome atmospheric pressure that's trying to keep everything inside your solution. And so that takes more energy. So the boiling point number, the temperature at which it boils, will be higher. Freezing point depression, similar idea, but it's now lower than normal. So what does that mean? A solution freezing point will be lower than the pure solvent. So if you take water, we know happens to freeze at 0 degrees Celsius. If you dissolve something in that water, it will freeze at a lower temperature. Okay, why is that? Well, think about what has to happen if you're making something freeze. The particles have to stop rolling around and they have to sit still, right? They have to sit in place. So the solvent is not as attracted to other solvent because it's attracted to the solute. So if you're trying to get the solvent to freeze, meaning it needs to attract to other solvent, you need to remove more and more and more energy so that solvent will attract enough to other solvent and stop rolling around with the solute. Think about what I just said. So to get something to freeze, the solvent and the solvent has to attract. But the solvent is already attracted to the solute. So you have to slow it down way, 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 way more. You're taking away more and more energy, meaning the freezing point is getting lower and lower and lower so that the solvent and other solvent particles will attract enough to stop rolling around like a liquid. Boiling point elevation, freezing point depression. Pause the video if you need to kind of process that. Make sure that makes sense about those colligative properties. All right, and then I have math equations to go with them. The first thing I want to talk about, though, is you have two kinds of solutions, non-electrolytes and electrolytes. So in a non-electrolyte, the math equation looks like this. The change simple, delta T sub B, so the change of temperature boiling, equals a K boiling constant times molality. So what this means is the boiling point of a solution equals the boiling point of a pure solvent plus the change of temperature boiling. So if I want to know what a solution will boil at, I have to figure out how much it's changing plus whatever the normal boiling temperature was for that solvent. And then we have that same equation for freezing, all the same stuff. The change of the temperature of the freezing solution will be a constant K freezing times molality. So if I want to know the freezing point of a solution, I take the freezing point of the solvent minus how much it changes. Because remember, it's freezing or boiling point elevation and freezing point depression. So these are the math equations. So just making sure we've got it. KB and KF are constants. Someone has done a lot of experiments and a lot of research, and we can just look these up. In fact, I'm going to give you the K values for water because we use it a lot. So the KB value for water is 0.512 degrees Celsius for every 1 molality that you have of a solution. The freezing K is for water is 1.86 degrees Celsius for every 1 molality of your solution. So then, of course, if you have more or a higher molality, you'll multiply it more, it changes more. But that fits our definition of colligative properties, right? If you have a higher molality, that's more particles that have to either be sped up or slowed down. So then that changes the temperature more. Okay, and then molality, remember, is moles of solute per kilogram of solvent. So just remember that it's solvent and its mass, not liters of solution. That is molarity. All right. Now, the only other option, I got one last thing here, is, well, what if it is an electrolyte? So notice what changed about this equation. You still have the change of temperature boiling equals the KB molality, but then there's extra little thing, I. And then same thing for delta T of your F. So exact same thing, only there's this little letter I in there. I is the number of ions. Because remember, colligative properties is all about how many particles are in there. So molality affects how many particles, how many moles per kilogram. But if it's an ionic compound that is split up, you have more ions, which would mean more particles that have to be sped up or slowed down. So that will change your temperature, boiling temperature, freezing. A little side note, if you're doing your own research or your own reading, sometimes this I is referred to as the Van 't Hoff factor. So like, what is the Van 't Hoff factor? Is really just asking how many ions are present. So that's something we'll talk about at AP Chem or other chemistry classes. I just want you to just have heard it at least. All right, let's do some examples to review what I mean by number of ions. Aluminum chloride. It has 1 aluminum positive ion and 3 chlorine negative ions. So total, there's 4 ions. 3 negative chlorines. They're all separate atoms, chlorine, 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 all -1, to balance 1 positive aluminum, 4 ions. But then something like this, there's 2 sodium ions balancing 1 sulfate ion. SO4 are not separate ions. SO4 is 1 ion that has a -2 charge balancing 2 separate sodiums. So this would be 3 ions. So what that means is you would need to know the molality of this solution. You would need to know the K value for whatever the solvent was, probably water, and then multiply it by 4. So you're going to have more change that happens because it was an ionic solution. So that's what I was just saying here. The reason we need to think about this sometimes is that there's more particles from the ions, so there's more particles to slow down or more particles to speed up, depending on if you're freezing or boiling, which will give you more change in your temperature, which will give you a higher boiling point elevation or a lower freezing point depression. That's why we had to talk about that. Okay, so that's a lot of deep info. Do you got that down? Let's do an example. So using boiling point elevation and freezing point depression, we can actually use those math equations to determine the molar mass of an unknown sample. And this is actually getting into what your pre-lab is going to be like, or what your lab is. So this is a pre-lab example, thinking ahead to the lab you're going to do this unit. So here's what I know. A non-electrolyte solution, okay, so good. We're not going to have to worry about the I factor. 5 grams of that unknown compound X in 60 grams of water will freeze at -1. Okay, well, water normally freezes at 0, so we know there's something dissolved in there. I want to figure out the molar mass of X. There's 4 steps that we're going to use. First, we're going to find our change of temperature. The change of temperature is 0 minus, because it's freezing point depression, -1, right? So the change of temperature is 1 degrees Celsius. All right, now we can find molality. We know the change of temperature is 1. We know the K value for water that was given to you in your notes, or you could look it up, is 1.86 degrees Celsius per molality, and then question mark molality. So we can solve for molality. So I'm doing basically 1 divided by 1.86. That gives me molality, and I get this number on my calculator. Okay, so I don't have to worry about sig figs yet because this number is not my final answer. So now I have my molality. Okay, but remember what molality really means. Molality is moles per kilogram. And if I'm finding molar mass, I want grams per mole. So now what I want to know is, well, how many moles, if this is the molality, how many moles of my compound are in 60 grams of water? So I'm going to take my 60 grams of water. I'm going to use molality as a conversion, but this conversion is moles per kilogram. So I have to get from grams to kilogram. So that's next. So grams divided by 1,000 grams will give me to kilograms. But then molality is 0.536 moles over 1 kilogram. So now kilogram goes away. So if I multiply these numbers on top, divide these numbers on the bottom, I get 0.032258, whatever, moles. Again, not worried about sig figs yet. Okay, so that was step 3, because I'm trying to find molar mass. Molar mass is grams per mole. Well, I already knew my grams, it was given. Now I just found moles. So step 4 is find the molar mass of X, grams per mole. The grams was the 5 grams I used in the example to make this solution. The moles was figured out because of the molality. I divide that out. Now I have to worry about sig figs. This has 1, 2, 3. This has 1, 2, 3. This has 1, 2, 3 sig figs. So my final answer can have 3 sig figs, 155 grams per mole. So then now what I would do is I would take this and put it in a database, get a list of all chemicals that have this as their molar mass, but then I would use my other properties. I know it's not electrolyte, so I get rid of any ionic compounds that have a molar mass of this. I would look at what this looked like. I know it's polar, at least a little bit, because it dissolves in water. So then I could get rid of any of these chemicals that are non-polar, right? So I have a polar molecule. I know that it's a molar mass of this, and then I could identify my unknown. And that's what you're going to do in our lab. So spoiler alert, that's where we're going with this. So I'm using freezing point and freezing point depression, the data that it is a lower freezing point than normal, in order to, and then I use this fancy equation. I did a bunch of little DA steps to solve my question. What is the molar mass of this unknown compound? And then I could use some science reasoning skills to figure out the identity. Whew, okay, pretty cool example, but lots of little details, right? So process that if you need to, pause the video, get caught up, make sure you understood what happened. We'll do some more examples like that in class. There's examples like that in your unit practice problems. But that brings us to the end of our notes for today. Go ahead and do a level 3 kind of question. Maybe you predict when I would need to use this, like make up a situation where I would need this. That might be a cool level 3 kind of question. Come on back when you're ready. So that is the end of our notes for today. So finish any CASA questions, write your summary. And then there are some unit practice problems that I highly recommend you do to get practice of what that stuff we just learned. So like using osmotic pressure, using freezing point elevation and freezing point depression and boiling point elevation. Check those problems, do them, check the answers, ask for help as needed. If you're watching this video for Try 3 class, your solutions practice should be done. The concentration FET activity should also be done. And then just remember that you can use office hours to get help as needed. Otherwise, I'll see you at our next Zoom meeting. Thanks so much for learning about chemistry with me. Bye.